Welcome. We are looking at momentum flux. We looked at rather rigorous way of analysis initially. We started looking at the microscopic level and taking things forward. And then somewhere in the middle, I told you something about a or dimensional analysis involving non-dimensional numbers. That doesn't have too much depth, let us say. It is based on one mathematical theorem, the Buckingham Pi theorem, and then it's based on practice. It happens to work. However, it gives us useful results. Although not rigorous, it gives us useful results. And then we went back to some rigorous analysis to get some insights into complex situations, the unsteady flow aspects as well as the pulsatile flow aspects. Let us look at turbulent flow. We'll still start out with a rigorous way of looking at it and then start making the various assumptions. We'll start relaxing things a little bit so that the approach becomes helpful rather than be rooted in rigor alone. Then we'll slowly move into more and more practice aspects. Our understanding may not be so complete or so much in depth, but it will be very useful. First, today, let us look at turbulent flow. We all know what turbulent flow is. We said there are two major types of flows. One is laminar flow, where the flow is in layers, the layers corresponding to the geometry of the system. The layers could be flat, the layers could be cylindrical, and so on. Or it is turbulent flow, where it is a chaotic flow with pockets of fluid tumbling over each other and flowing. We saw Reynolds number, which is a means by which we could distinguish between laminar flow and turbulent flow. The laminar flow conditions, the flow in layers, occurs if the Reynolds number is less than a certain value, and if it is greater than a certain value, it is turbulent flow. That particular number depends on the situation. For example, for flow through circular pipes, cylindrical pipes, the number that we'll be using this course is 2100, below which the flow is laminar, 4000 above which the flow would be turbulent, and that is well known. So let's move forward. Many flows in the bioindustry are turbulent. Okay. Flow in pipes, flow in the bioreactor, flow in separation equipment are usually turbulent. And they are preferred that way in the industry because it provides better mixing, which is necessary for optimal production, optimal operation, and so on and so forth. Turbulent flow can occur near artificial valves of the heart sometimes, and that leads to wasteful expenditure of pumping energy. The heart is the one that's providing the energy for pumping, and that's wasteful expenditure of pumping energy. I would like to invite you to watch this video. It's the title is Whole Blood Viscosity, Links to Cardiovascular Disease. It's available free. Please watch this video. This will give you a good idea between turbulent flow and cardiovascular disease. It shows you nicely how the turbulent flow could cause cardiovascular disease. Please take a look at it to appreciate where all the turbulent flow is relevant. You just need to look at it appropriately. You'll find turbulent flow where the appropriate flows are occurring. What you're going to see in this chapter is how to approach the analysis of turbulent flow. Let's begin. Okay. Let's start very simple. The velocity Vz could be this direction. We'll stick to this for time being. Vz is the velocity at any point in turbulent flow. Okay. And that can be expressed as an average component and a fluctuating component, the sum of those two things. Okay, that's reasonably general. Okay, it's a good strategy, and that's reasonably general, and this works very well, as you would see. Okay, so this would be one aspect of our approach, to view the velocity at any point at any time as consisting of an average component and a fluctuating component. If this is not very clear right now, it will become clearer maybe a couple of slides down the line. We will spend more time on this aspect. People, researchers, through careful experimental measurements, they have shown for the flow in a pipe, the following is valid in turbulent flow. The ratio of the average velocity to the maximum velocity, they found, or the velocity to the maximum velocity ratio, they found it was proportional to 1 minus r by r to the power of 1 by 7. Okay, this is in turbulent flow. This is through measurements, right? They went and measured the velocity at each point in a cross section, and they found this to be valid. The average component divided by the maximum velocity of the average component is related in this fashion, raised to the power of 1 by 7. We know that in the laminar case, you go back to your into your notes and look at it, you will find that Vz by Vz max was 1 minus r by r the whole squared, the parabolic velocity profile. Okay, so Vz was Vz max times 1 minus r by r squared. Therefore, this ratio is this. So you can find the difference between laminar flow that we have already seen in great detail and the turbulent flow which we have started looking at in this chapter. We'll call this equation 3.8-1. The average of the mean component to the maximum velocity, that ratio, people found through measurements to be 4/5. Whereas we recall from our earlier notes, what was it for laminar flow? Yes, half. Okay, go back into your notes and check. It will be half. Also, one more. This is 3.8-2 before. The pressure drop, delta P, that is PL minus P naught, or even if you don't take that negative sign and so on, is proportional to the flow rate per 7/4. That's what people have found through experiments in turbulent flow. In laminar flow, if you recall the Hagen-Poiseuille equation, it was directly proportional to Q. Okay. Let's call this equation 3.8-3. So there are differences, wide differences in the relationships between laminar and turbulent flow. You could watch these videos. This gives you an idea of how the turbulent flow occurs when the flow is open in a river or something like that. And in a tube, this video gives you how the flow appears. You'll have a means of clicking these easily through, I think there should be a file that you could download with these links, and you can go and click these links. As we have already seen, the visualization of turbulent flow, the turbulent flow can be visualized as a random motion of pockets of fluids, and those pockets of fluids are called eddies. Eddy, singular, eddies plural. Turbulent flow in a tube, the flow is entirely random at the center of the tube, far away from the wall. Near the wall, the cylindrical wall, the fluctuation in velocity in the axial direction is greater than the fluctuations in the radial direction. Okay, we are looking at this tube. This is the radial direction all over. This is the axial direction, through the direction in which the flow is occurring. And the fluctuation in velocity in the axial direction is greater than the fluctuations in the radial direction. The V dash, the fluctuating component, is higher in the axial direction compared to the radial direction. And at the wall, the fluctuations are 0. Okay, the layer closest to the wall sticks to the wall, it doesn't move, and the fluctuations are 0. Now, let us consider the fluid behavior at one point in turbulent flow in the tube or the pipe. We are going to use pipe and tube interchangeably in this course. Let us say, as we are watching it, there is turbulent flow that's occurring in the pipe. As we are watching it, we are going to slowly reduce or decrease the pressure drop which is causing the flow. Okay, you could do that by changing the motor settings, pump settings, and so on and so forth. So we are going to decrease the mean velocity by causing a pressure drop change or a decrease in the pump speed. The variation in the axial component of the velocity Vz at any point of the observation, because this is velocity in various directions. It has a predominant axial component, but it could also have other components because of the fluctuations. The variation in the axial component Vz at the point of observation would be something like this in a plot of Vz, this is the velocity at any time, versus time. Okay. So it is going to be like this and so on and so forth. Then the pressure drop is being slowly reduced, and therefore the velocity will also slowly reduce, whereas the actual velocity would fluctuate something like this. Okay, this would be the trace of the various measurements of the velocity Vz, the axial component, at any point. Okay, so this is what I meant. So if we draw an average of these various points, it will look something like the dotted line. Okay, the dotted line gives you the average of this profile, of the values in this profile. So this is what we mean by the average component, Vz dash. Okay. So Vz dash is called the time smoothed velocity. That is the average Vz over a time interval large enough with respect to the time of turbulent oscillation. This, let us say that we are taking an average over this TA. Okay, so at each point we take an average over a certain neighborhood, and this time interval is large enough with respect to the time of turbulent oscillation, but small enough with respect to the changes in the pressure drop that is causing the flow. The pressure drop is slowly reducing, the velocity, the average velocity is slowly reducing, but the fluctuations are much, much faster. This time TA is much higher, is much larger compared to the characteristic time of the fluctuation, but is much slower compared to the time of the change in pressure that's causing the flow, or the velocity that's causing the decrease in velocity, that is. So Vz bar, the average velocity, is formally defined as 1 over TA, the time interval here, integral of t to t plus TA from here to here of Vz dt. Okay, this is the definition of the time smoothed velocity, or what we call the average, what we called the average component earlier. We will now onwards call it time smoothed velocity. So the velocity at any point is the sum of a time smoothed component and a fluctuating component. We'll call this equation 3.8-4. So Vz is equals Vz bar, the time smoothed component or the average component, plus the fluctuating component Vz dash. Equation 3.8-5. The pressure at any point will also vary in a similar fashion. Okay. So this is the pressure at any point in the fluid. So we can write pressure in general as the sum of an average component and a fluctuating component. Okay. Equation 3.8-6. We are going to manipulate this average component and fluctuating component. So let us try to understand them a little better. If we take the average of the fluctuations, by the very definition of average, the positive values will always cancel out the negative values. That's the whole point about the average. Okay. So if you sum all the positive variations, they will cleanly cancel out the negative variations if we take the average. That's the definition of the average itself. Okay. So we cannot use this, the average of the fluctuations, as a measure of anything, because it's going to be zero. So if you are looking at the measure of the fluctuations, measure of the turbulence and so on and so forth, we cannot do this. We'll have to do something else. The mathematical trick here is we square them. We square the averages, we square the fluctuating components Vz dash. When we square them, the negatives will also become positive. The square of a negative is a positive. Okay, so we'll have the sum of all positive fluctuations, and then take the average over all the squares, and then take the square root of it. Okay, so that way we avoid the difficulty of the positive terms cancelling out the negative terms cleanly, and we will have a measure that we can work with, and what better measure than the fluctuation in velocity itself. Okay. So this or a modification of this can be used as a measure of turbulence. In fact, the intensity of turbulence, which is a measure of turbulence, is defined as the square root of the fluctuating velocity squares the average of the fluctuating velocity squares, which means you take the fluctuating velocity, you square it, then you add all the squares and then take the average. Okay. This, and of course, if you take the average, it will be a square term. The units would be velocity squared, and therefore you need to take the square root to get it in the units of velocity. So once all that is done, you divide it by the average velocity, and that is called the intensity of turbulence. Equation 3.8-8. The typical values of the intensity of turbulence are between 0.01 and 0.1, just to give you an idea. And near the wall, as we mentioned, the axial intensity of turbulence would be much greater than the radial intensity of turbulence. At the center, there would be a lot of fluctuations all around, totally chaotic flow. But closer to the wall, the axial fluctuations are going to be greater than the radial fluctuations. At the center, it's anisotropic conditions where they are comparable. As long as the eddy size is greater than the mean free path of the molecule, okay, which means the concept of a continuum holds, the following fundamental aspects need to be applicable for turbulent flow. If you are able to use or apply the continuum aspects, the fundamentals of continuum aspects need to be applicable. So whatever we have developed, material balance, energy balance, material balance, momentum balance, and so on and so forth, they would certainly be applicable here. They are, universal principles. It doesn't really matter what kind of flow there is. Okay, so that is the beauty of holding on to such principles, and that's what this course gives you. So the equation of continuity that's based on mass balance, as well as the equation of motion that is based on momentum balance, both need to be valid. So for turbulent flow, let us consider incompressible turbulent flow for illustration. If you need to get into compressible turbulent flow, you can go and pick it up from some advanced texts. So incompressible turbulent flow, the equation of continuity can be written as, instead of wherever we had a Vx, we have a combination of an average component or a time smooth component and a fluctuating component. That's all, right? The equation needs to be valid. So we substitute Vx bar plus Vx dash for Vx, Vy bar plus Vy dash for a Vy, and Vz bar plus Vz dash for a Vz. So the same equation must be valid. So this equation of continuity will be valid. It's incompressible flow, so del dot V equals 0. So this is what del dot V is. This is only for illustration, okay, to tell you that this kind of a formulation works. Then you could go and make density variable and work out the various details. In fact, look at a book. That might be easier. This is equation 3.8-9. And the equation of motion, again, let's look at only the x direction. Okay, then you can extend it to the other directions. Is going to be something like this. It's the equation of motion, which I've written. The only thing that I've done is put in Vx bar plus Vx dash for the velocities and P bar plus P dash for the pressure. That's all. Okay. So this equation would be valid, dou t of rho Vx bar plus Vx dash equals minus dou x of p bar plus p dash minus dou x of rho times the product of these two velocities plus dou y rho product of Vy component. This is the x direction, therefore this would always be Vx, as we have seen there, plus the shear terms mu del squared. Instead of a Vx here, we have Vx bar plus Vx dash plus rho Gx. Okay. These equations need to be valid. The number is 3.8-10. Now, if we take the time average of the velocity components, okay, this is a very standard thing that we do whenever we take such approaches. We average over short times. So V bar is nothing but 1 by Ta integral of 0 to Ta v dt. And we are going to take the time average over TAs that are large with respect to turbulent oscillations but small with respect to the micro variations, is not macro variations, small with respect to the macro variations, the change in pressure and so on and so forth with respect to the macro variations. And if we time smooth the equation, that's what this is called, if we do this procedure, the time average fluctuations will go to 0, okay, because we're taking a simple average. And the time smooth equation of continuity, please write this and check this. I'm not going to derive that here, but this is how this equation, okay, this equation, when you take the time smooth average, will become whatever equation I'm going to write. Okay, the variation in these would go to 0 when you take the time average. Time smoothing when you take the time average, that's going to go to 0. So it will have only the average components, dou x of Vx bar plus dou y of Vy bar plus dou z of Vz bar equals 0. Okay. Equation 3.8-11. Also, the time smooth equation of motion will turn out to be this. Okay, there are a lot of steps between the previous equation where I had written V as V bar plus V dash to this. Okay, I'm asking you to work that out. If you have difficulty, you can get back to me by the forum, the course forum, or an email. The time smoothed equation of motion would be something like this. Okay, it will turn out to be something like this because of the time smoothing of the fluctuating components going to 0. So we get dou t of rho Vx bar equals minus dou p bar dou x minus, you have the product terms here, rho Vx bar and so on, minus dou x of these terms will come in. Why? Because when you take the fluctuation and take the average, that goes to 0. But what are these? These are products of the fluctuations. They will not go to 0, right? So, for example, we are taking the product and even the negative would become positive and so on. And therefore, the product will not go to 0. And this is just not the product. You're taking the product of the fluctuation, Vx bar, and taking an average of those. Those terms will remain, okay, when you work things out. So, this would be an extra term plus mu del squared Vx bar plus rho Gx. Equation 3.8-12. Okay. So, apart from this term, the rest of the equation is the same as that we got earlier. Okay. Only this term is the extra term compared to the equation of continuity for laminar flow. Here, in this case, it does not matter. It is a simple time smoothing that we do. The fluctuating components will go to 0. Here, since the products happen and the average of the products of the fluctuations happen, that is not going to go to 0 and that term will remain. Now recall that rho Vv was momentum flux. Okay, we have already shown this. And the momentum flux we saw in the very beginning of this chapter is nothing but a stress, okay, force per unit area. And therefore, let us say that this component tau xx bar t for turbulent equals rho Vx dash the bar of that product. Okay. In other words, we are giving a certain meaning to this term, okay, in the context of what we know already. So rho Vx bar Vx rho Vx dash bar is what we're going to call as tau xx bar t. Okay, this. And similarly, tau xy bar t equals rho Vx dash Vy dash bar, and so on. Okay. Why are we doing this? We are trying to write it of a form that we are familiar with. You could recognize that there were three such things for the x direction, there would be three such things for the y direction, there would be three such things for the z direction. Therefore, they can be considered as the components of a turbulent momentum flux tensor, tau t, tau bar t, and that's a flux tensor, therefore there is a squiggle on top. Okay. So, these stresses are actually called Reynolds stresses that arise because of the turbulent nature, and that's only a term that was different from laminar flow. So in vector notation, the time-smoothed equation of continuity is going to be the same as that for the laminar flow. Only thing is that in this case, we are taking the time-smoothed component. In the laminar flow, it was the actual component. And the time-smoothed equation of motion is going to be rho d dt of b bar equals minus del p bar minus del dot tau, the laminar shear stress tensor, minus del dot tau, the turbulent shear stress tensor, plus rho g. Okay. This is equation 3.8-14, and compared with the laminar flow situation, this is the only extra term. So equations 3.8-9 to 14 are valid for an incompressible flow. On the same lines, it can be shown that the equations or tables for laminar flow are valid for turbulent flow if only we could replace Vi by the time-smoothed average Vi bar, if we replace P by the time-smoothed average P bar, and the tau ij that we had earlier, we need to replace by a certain laminar component and a certain turbulent component, the Reynolds stresses. Okay. If we do this, the same equations that we had earlier can be used. Okay. It will get complicated. I'm not saying it will be easy to handle, but we have approached it. We have a means by which we could describe turbulent flow. Now, to get a velocity profile, we need a relationship between the shear stress and the velocity gradient. Okay. In the case of laminar flow and a Newtonian fluid especially, we had our Newton's law of viscosity, which gave a relationship between shear stress and the velocity gradient. We don't have that luxury here. Okay. Let me read this out. For laminar flow, we had a theoretical base in terms of constitutive equations, the Newton's law of viscosity. We don't have that kind of a thing here. However, what people have done is, based on a large number of experimental studies, relevant expressions have been proposed. Relevant expressions for the relationship between tau and the velocity gradient have been proposed. And I'm just going to present two here, just to give you a flavor. What people did was, familiarity is nice, and therefore they first formulated one that is similar to a Newtonian fluid. But this is a turbulent case. So tau yx bar t equals a certain mu t times minus of dvx bar dy. Okay. This looks similar to a Newtonian fluid. However, this mu of t is nowhere close to that of a molecular viscosity. Okay. The form is fine, it works fine. Only thing is that you cannot rely on molecular viscosities. In fact, the turbulent viscosities could be hundreds of times the molecular viscosity, typically. Okay. Equation 3.8-15, but this formulation allows us to have certain insights. This mu t is called the eddy viscosity, and it could be hundreds of times the molecular viscosity. A second relationship, a popular formulation was given by Prandtl a long time ago. And for doing that, he assumed that the eddies in the fluid move around in a fashion similar to that of molecules in a gas. And therefore, the gas kinetic theory principles can be brought in here. A mixing length L, which is a function of position, represents an idea similar to the mean free path in the kinetic theory of gases. Mixing length L in the liquid is equivalent to the mean free path. And therefore, taking that into account, Prandtl proposed a tau yx bar T equals a minus rho L squared dVx dy absolute value, this is a viscosity component, times the velocity gradient there. Okay. Equation 3.8-16. And let's not spend too much, much more time. Just two formulations to tell you that these are available, many more are available, you could use them. What is typically used is an empirical relationship. For flow in pipes, tubes, the velocity profile in turbulent flow can be obtained through Diesler's empirical formulation. Through a large number of experiments, Diesler came up with these relationships, and these can be used to get the velocity profile in turbulent flow in pipes. To get to that, let us first define a V plus as, a variable V plus as the ratio of a Vz bar, the time smooth component, and square root of tau 0 by rho, the wall shear stress by the density. Okay. This, as you can, if you can work out the units, dimensions, you will find this is dimensionless. Similarly, he also defined a S plus, which is defined as S times square root of tau naught by rho times rho by mu. And S is nothing but the differential distance, that is, you take the radial distance, the distance of the wall radius, and you subtract the radial distance from it. Okay, R is the wall radius minus the radial distance, or the radial distance from the wall is represented by S. Okay. So S plus is what the formulations are in terms of. Tau naught is the wall shear stress at S equals 0. What Diesler found was that for S plus greater than 26, this is by experiments, therefore don't worry about these odd numbers, this is what was found, this is what was revealed by experimental data. V plus equals 1 by 0.36 ln S plus plus 3.8 works. Equation 3.8-17. For S plus being between 0 and 5, both inclusive, then V plus equals S plus. And for S less than 26, 0 to 26, then you have a complex relationship, V plus equals integral 0 to S plus ds plus, the integration here is 1 by 1 plus n squared V plus S plus times 1 minus exponential of minus n squared V plus S plus. So this empirical formulation can be used to get the velocity distribution in turbulent flow in pipes alone. Okay. Remember, this was from a set of experimental data, therefore it will be valid only to that condition. We don't have the luxury of fundamental understanding where we can apply with confidence with our eyes closed to any situation. That is what we could do earlier. We cannot do that here because we don't have an understanding. However, we need to move forward, and therefore we use such aspects which could have certain limitations, but which are useful if the conditions fall into those limitations. I think that's all I have here. Before that, n is the Diesler's constant for tube flow near the wall, empirically found, experimentally found to be 0.124. Okay, that is good enough an introduction to approaching turbulent flow, starting from fundamental aspects and then some empirical aspects we looked at. Let's stop here for this class. We'll meet again in the next class. See you then.